Okay, so as I promised last time, we're going to look at a couple of bits of experimental data that also suggested that something not comporting with classical physics was going on. Okay, so this was in the early days of the development of quantum mechanical theory, which is quantum theory. And this effect, the photoelectric effect, just to give you a little context before we walk through it and why it gives the evidence that it does, is something that was observed right around the turn of the century, just into the 20th century. And the experimentalists at the time didn't have a good idea of how to explain what they were seeing. And in 1905, Albert Einstein wrote one of his famous papers that decade, in which he explained the photoelectric effect as in the context of quantum theory. There, that's what I'd like to say. And he actually won a Nobel Prize for this in 1921, and sort of solidified, it was one of the things that solidified Einstein as sort of one of the, well, at least at the time, one of the greatest living physicists. Okay. So, the photoelectric effect, as it says in the headline there, it's one of these phenomena that suggested that interpreting light solely as a wave was incorrect. So last time we talked about the two-slit experiment, and we talked about how electrons behave as waves, or have wave-like properties in addition to their particle-like properties. And the photoelectric effect is an experiment that suggested a similar thing about light, except that at the time, Maxwell's equations described light very well as an electromagnetic wave, and the theory was reasonably well understood, and it made all sorts of predictions about what should happen. For instance, in this case, where we have light at a single frequency, so say some red light at a particular wavelength and frequency, coming in, hitting a metal film, and metal has a lot of conducting electrons in it, so electrons that are bound to the metal but are free to move within it. And Maxwell's equations and the wave theory of light, or wave description of light, had some concrete predictions on what should happen when you shone light on this metal. However, the results of the experiment did not line up with what those classical equations for the behavior of an electromagnetic wave were telling scientists, physicists, what should happen. And what did happen is that below a certain frequency, no electrons would be released. Right? So if you had an appropriate piece of metal and you had light of an appropriate frequency, then you could cause light to be absorbed by the metal and have, as a result, electrons freed from the metal. So instead of being bound to the solid, you get a free electron just going off wherever, okay, until it encounters another charged object or something like that and gets attracted to it or repelled from it or whatever. So, in classical theory, the idea was that the frequency really shouldn't matter. It should matter, what should matter is the intensity of the light, because the idea was that the electrons would sort of build up energy over time as you bombarded it with more and more electromagnetic waves, and that would eventually cause the electrons to gain so much energy that they could pop out of the metal and go wandering off. But that's not what happened. Below a certain frequency, okay, and the specific frequency there, that cutoff between no electrons being released and electrons being released, was something that was dependent on the type of metal that was being used. Okay? And as they turned up the frequency, at the time they used like a really hot, like light bulb kind of thing, and then used a series of filters to get rid of all of the light that, at different frequencies from the one that they wanted. Okay? Now above that certain frequency, electrons would be released, and freed electrons would have more energy the larger the frequency became. Now we've actually already looked at an equation that implied, even if we didn't really talk about it, but implied the particle nature of light. We said that a photon of light had a certain amount of energy, so E here, that was dependent on the frequency, so F, of the electromagnetic wave that it corresponded to. And that right there is a little bit of a head scratcher because you're talking about frequency, which is definitely a wave thing, and yet you're talking about the energy of a little corpuscle, a little bit, a little particle of light, which we call the photon. So you have the particle and wave-like property of light represented in a single equation there. And what this equation tells us, and is something that Einstein predicted in his 1905 paper about the photoelectric effect, is that the energy of the photon is linear in frequency. And that's why when you were below a certain frequency, well, there just wasn't enough energy in any of the little particles of light to kick one of these electrons out of the metal. It turns out a specific type of metal, gold or aluminum or whatever it happens to be, has a what's called a work function, and it's a fixed amount of energy that must be given to an individual electron before it can be freed from the metal. And if you're just bombarding it with a whole bunch of low energy photons, well then the photon hits the electron and isn't absorbed, okay? And it just doesn't impart enough energy to get it out of the material until you have a certain frequency that gives you enough energy which matches the work function of the metal, which allows you to bump electrons out of the metal surface, okay? So, this suggested, contrary to all of the theory at the time, that light had both a particle nature and a wave nature. The wave part was pretty well understood via Maxwell's equations, and the particle thing was what differentiated it. In the classical theory with the wave nature of light, again, you would expect that the frequency really wouldn't matter, because in that you are continuously delivering energy to the surface and the electrons would eventually absorb enough and they would be kicked out. Whereas here, what it is essentially a flood of little photons of light, and if the energy of individual photons of light, which are the things interacting with the individual electrons in the metal, doesn't exceed this threshold for kicking electrons free of the metal, whatever the metal is, then you just don't get any electrons being freed. Wild. Okay? Now, another thing that, again, around the same time suggested that there was something going on that did not comport with classical theory was the idea of, or the phenomenon of atomic spectra, or spectrums. Okay? And remember back to our model of the atom. If the first one that's usually introduced when you're introduced to atoms in school is that you've got a nucleus made up of all these protons and neutrons, and then you've got all these little BBs, all these little particles, these electrons that are orbiting that nucleus, kind of like planets going around the sun or something like that. But we know now that that picture of the atom is not correct, and the classical theories at the time predicted that, well, maybe they knew that there was, something around the atom, though the electron wasn't discovered until right around the turn of the century as well. Okay? But they had all these theories that predicted that essentially the energies of the electrons around a nucleus should be more or less continuous. In other words, they could take on lots of different values, and the particular value that an electron would have could be any in a whole range of values. So instead of having to be like, just to sort of try to illustrate the point, instead of being specifically 1, 2, 3, 4, or 5, then it could be anything, any little sort of real number, any fraction of any of those. Okay? But that's not what they saw. Now in this simple experiment where you have a light source, if you're looking at, let me switch to the, get the pen. If you're looking here, okay, so we've got just a white light source, like an incandescent bulb. You send it through a slot, and then you send it through a prism, and then you project it on a screen. What you get is this sort of continuous band of colors, okay? So that's okay, that's continuous. That suggests that all of the little bits of light that are coming off of this bright filament can have lots of different energies, and nothing's really wrong there. But then if you look at a fluorescent light, okay, so over here, remember what well, maybe we haven't talked about what a fluorescent light is, but it's a mercury vapor arc lamp, but then has like a phosphor coating on the bulb that turns it into white light. Mercury vapor has sort of a purpley bluey kind of color by itself. And then that phosphor absorbs all of that mercury vapor light and then re-emits it to create something that looks white. When you actually send it through a slot and send it through a prism to sort of break it out using chromatic dispersion, something we just talked about earlier in the course, well then you don't get this continuous spectrum. You get these very specific lines, these very specific colors of light. So instead of being continuous, any particular value, in between value x and value y, you have it taking on the energies of very specific things. Okay? So let's flesh this out a little bit. Okay, and that was problematic. There was all kinds of attempt. One of the first one was called the Bohr model, to try to explain why atoms of, say, mercury or whatever it is, when they were excited and then the electrons would come back down and kick out photons of light, why it would be that those photons of light would be these very specific energies and thus very specific colors versus any old thing. Okay? So first, let's reduce this kind of experimental thing over here on the right to something that we can see here, sort of a diagram. If you imagine you have a hot source, so say it's the sun or the incandescent bulb over here or something like that. If you just look at its spectrum straight up, okay, well then it's going to emit at all kinds of different colors. Okay, just like the sun does. We looked at the spectrum of the sun, right? And it has a peak around green, and then it falls off on either side, so you get a whole bunch of different colors if you're just looking at the visible light. Okay, but if you then look at the spectrum of the light from the hot source, again, the sun, an incandescent bulb, something like that. But first, that light has passed through a gas that absorbs it. Well, then what you find is that there are a whole bunch of very specific places in this whole spectrum. So very specific energies. Remember that color is related to frequency, and frequency is related to energy for light. Very specific frequencies, very specific colors, very specific energies at which the gas is absorbing bits and pieces of this continuous spectrum that comes from the hot source. And if you were to then examine the gas, which has been excited, sort of absorbs some energy from the light of the hot source, you just look at the gas as that energy is radiated back out as light, well then you get kind of the inverse of the spectrum that you see here. So this is called absorption spectrum because you're looking at what's missing because of the absorption of the gas. And this is called the emission spectrum because it's the colors of light that when you've poured some energy into the gas from the hot source, then it will emit at those same sort of missing spots up here. Okay? So you'll see a whole bunch of different things. You've got a cartoon, well not a cartoon, but a different set of absorption and emission lines over here that demonstrate that same kind of thing. So over here would be the absorption, okay? Over here would be the emission, and this would be the original sort of just hot object, sun, incandescent object, some other star, something like that, that continuous spectrum. Okay? So the idea that this gas could be hydrogen gas, could be mercury vapor, could be helium, could be neon, it would emit at these very specific energies was something that was completely unexplainable by classical theory. There's no particular reason why it should emit at these very specific energies. And as with anything in physics, physicists, that isn't explained, physicists tried very, very hard and in relatively short order, over a couple of decades, came up with some explanations, and this also was part of this general quantum theory that was developing in the earliest 20th century. And the idea was that the energies that the electrons could have in existing around the atomic nuclei were quantized, quote unquote. In other words, for any atom of, say, hydrogen or helium, the electrons in all of the orbitals in that cloud that we talked about earlier in the course around the nucleus would only have specific energies associated with the orbits. Well, orbits is about orbitals, okay, so the place where they were most likely to be. So in schematic, what that looks like is this. You have the nucleus here, okay, and you kind of schematically put them in as orbits, if you like, okay, except you can't get into your head that the electron is just whirling around here at a particular place in time, because remember the previous discussion where it has a wave function, which only tells you about the probability of it being in a certain place. However, because of the way that it's bound to the nucleus, right, nucleus having positive protons and the electrons being negatively charged, so bound to it by that electrostatic attraction, those electric forces between those two things. Because of that binding, the electrons around the nucleus can only take on certain energies. And so when an electron that's absorbed some energy and been kicked up here into a higher orbital, so to speak, when it releases that energy and goes back sort of to its normal state, well then a photon, let me change colors here, a photon of a particular energy, the difference in energy between those two orbitals, gets kicked out. Okay? And that's what's happening when you the gas here is absorbing, so the electron is, say, starting here and absorbing some energy and getting kicked into a higher energy orbital. And then that shows up in the absorption spectrum because that particular energy of photon has been absorbed by the gas. And then if you look at the emission spectrum of the gas, well, then that is the result of the electron hanging out here. But remember that we generally only stay in sort of this excited state for a little while. And so when it jumps back down to where it was, that photon of energy comes out. And that corresponds, right, that energy right there corresponds to the energy of one of these spectral lines, as they're called. Okay? So quantum theory gives us an idea that things, including light, including the energies of electrons in atoms, as it turns out the energies of electrons bound to molecules, all sorts of quantum objects are quantized in terms of their physical properties, in terms of how much energy they would have, and how much charge, etc., etc., etc. So we'll cut it off there because we're coming up on 20 minutes here. And when we come back, we're going to talk a little bit about what happens when you stack a whole bunch of atoms together. And when you do that, you still get this quantization, right? These very specific energies that the electrons can have. And in the case of materials called semiconductors, this creates what's called a band gap. And a semiconductor the semiconductor materials are the bedrock of a lot of modern technologies that we deal with every day. So thanks for your attention. I will see you for that one soon.